So, given that it's 2 o'clock, I guess we might as well get started. So, when I was thinking about what I should be submitting as a topic for this year's Cauldron, I came up with a great idea. Why not talk about LLVM, the GNU Cauldron? Ooh. So that's what I'm doing, and we'll see how it goes. So the background is, actually we're working on, in my group, we're working on supporting the IBM Z, which is the mainframe, and you have a nice picture of one right here in front. It's about this high. And we've been supporting Linux on the mainframe for a long time, since about 1999, and we've been supporting GCC for a long time, and a somewhat shorter time. We are now also supporting LLVM, and as it happens, I'm actually maintaining both the IBM Z backend in GCC and in LLVM, so I'm sort of familiar with both worlds, and that's why I thought it might be a good idea to just talk about sort of my experiences, both on, and let's just go to the next page here. So what I'll talk about is sort of first from a sort of general perspective, what are we doing? What's the feature set we support in GCC versus what we support in LLVM? What have we been doing in both compilers to support both our ISA from an architecture perspective, and also, of course, the microarchitecture of the various processes we support. And then, I guess, probably the most interesting part for many of you, and that's why it's last here, is the performance results, so you have something to look forward to. And sort of that's sort of looking, all of that is looking from the outside, and the second part is then sort of looking a little bit from the inside. As a developer of a backend in GCC and LLVM, sort of how does it feel to work with these two software systems, if you will? And if I have time, I'll try to go through and see at least a small example, build it with GCC, build it with LLVM, and run through the various passes and the internal intermediate representation stages and so forth, so that we can get a little bit of a feel of how, what's similar and what's different. Now, I guess everybody here probably will be familiar with GCC, and probably everybody also will at least know what LLVM is, and I know some of you are probably more familiar with LLVM than I am, but so let's just get started. Yeah, I guess I put those charts in, but I think everybody here actually knows what LLVM is, so I can. Anybody does not know what LLVM is, let me know, and I'll go through. Otherwise, I'll just skip those and just talk about what we have been doing on IBM Z. As I said, we support GCC forever, and it's been upstream since actually 3.01. We missed 3.0 for FSF copyright assignment paperwork reasons, but it was in 3.01 in 2001. There have been, I just counted, 18 major releases since, every one of which worked fine on our platform, I hope. On the LLVM side, we have been upstream since 3.3, which is only 5 years ago, 2013. But still, there have been 9 major releases since they do a major release twice a year, while GCC is about once a year. Both are under somewhat active development, so 11,000 commits. But I just did a quick count of the commits in the config S390 directory, and similar on the LLVM side, so that may be missing some special stuff, but just as a general notion, both since we contributed the initial versions upstream, both sides have been under ongoing development, mostly from our team that's been listed here. So unfortunately, the way things are, we don't tend to get a lot of contributions from non-IBMers to the IBM C backend because, well, machines are too heavy. Most people don't have one of those in their basement, but so yeah, and so I listed sort of the main contributors. Not all of them are active anymore. So Hartmut did the initial part on the GCC side when it was still private, and has been one of the maintainers in the beginning. But he is actually no longer with IBM. The LLVM side, the initial development of the backend was actually done by Richard Sandiford when he was still with IBM, but he's no longer with IBM either, and he's no longer working in LLVM, but back to doing GCC work now. So as I said, I'm currently maintaining both. On the GCC side, most of the day-to-day business is actually done these days by Andreas Krebel, who is also a maintainer. So I'm so I'm no longer doing a lot of the code contributions on the GCC side, but so we still have a few other people. As I said, most of them IBMers or paid by IBM as contractors or via Bounty Source or some other stuff. So now in general, we try to support everything on both sides, with some exceptions where we made choices. So in the GCC side, of course, initially we had a 31-bit system. It's not, well, can call it 32, but for historical reasons, the pointers are just 31-bit size, because you need 1 bit to tell the architecture that it's not the 24-bit addressing mode. On LLVM, but since 2000, we also have 64-bit, and now most distributions have dropped or are in the process of dropping the 31-bit support, so it will be 64-bit only in the future anyway. And in LLVM, we just from the beginning said we are 64-bit only, and that's it. Similarly, of course, on the GCC side, we support a lot of older processor architectures. We just deprecated and removed 2 very old ones. So we did support 2 more, which was G5 and G6, which actually right now have been removed just a couple weeks ago, I think. But still, we support 8 architectures on the GCC side, and we only support, well, but at least we support already 5 of those 8 on LLVM. We do support all the standard languages that GCC supports. The GCC supports LLVM, and the Clang side supports the C family. There is right now no upstream Fortran. Hopefully there will be at some point. And there's no Ada, and there's some sort of Go, but we don't. That's not upstream, and we don't support it. On the other hand, on the LLVM side, we have at least 2 languages that really are only supported by LLVM, which we do support in our platform as well, which is Swift and Rust. Swift because it's important to Apple and some of our users as well, and Rust for things like, I guess you now needed to build Mozilla Firefox and some software that we want to have. Yeah, go ahead.
Quick question. Do you support PL8 on the GPL8?
Well, we support it as well as we ever did, which has never been public. So, but yeah, we do still use, internally we still use GCC to build PL8 code. But there's going to be, I mean, less and less code is actually PL8, so they're moving some of that code base away. We do support sort of extensions, so we have the vector extensions, which is sort of like LTVec, a little bit different. We support it on both sides with hopefully identical syntax most of the time. We do support a set of built-ins, again, mostly the same set on both sides. We do support the runtime libraries like libc and C++ and the GCC on the GCC side, of course. Right now, we don't support the libc library in LLVM because so far we have seen no use because we only have Linux, and Linux always brings the libc and C++, which works fine with Clang code, so there's been no need so far. LLVM has its own assembler and disassembler, which we now fully support, so every single instruction is supported by the integrated assembler now up to C14. Of course, on the GCC side, we have the separate GNU Tools, which provides this part. Similarly, LLVM does have a linker, which is sort of still under development. It works on some platforms. It doesn't really work completely on other platforms. And we have not supported it because, again, so far we have seen no use case for it. I mean, we could. It's a matter of implementing relocations, all kind of stuff. But so far, we haven't done that. We did implement the debugger. So I did implement the platform support for IBM Z in LLDB because we have a use case, and that is, again, has to do with Swift, because Swift has a interpretive environment, which they call the REPL, which is internally based on LLDB to actually run the code. So that's why we're supporting it. And of course, we do support the LLVM as a JIT, which is an important use case in LLVM. I guess in theory, you can also use GCC as a JIT, but there don't seem to be so many users of that. Talking about use cases, of course, it should be obvious, but I think it can't hurt to say it. Of course, the use case of GCC is that just about everything is compiled with GCC, and that's not going to change anytime soon. It is the system compiler for all Linux distributions. It is the system compiler for actually, we do support one other operating system, which is TPF, which is an IBM operating system, used for stuff like airline reservation systems and the sort of some niche products, where GCC also is the system compiler. And beyond the system, actually, most other software you can get for Linux on Z, whether from IBM, from some third-party ISVs, is also built with GCC. So that's not going away. On the other hand, we do have use cases for LLVM as well. So on the one hand, there are some use cases that need the LLVM JIT, and we want to support those. In the distros, I guess the main user right now is Mesa with the LLVM pipe stuff, which we use for remote display. And there's various ISV softwares which also use LLVM-based JITs, for example, databases and other products. The other thing is, as I mentioned, Swift and Rust, which we want to support, and we need LLVM for that because there's no other compiler for those except the ones based on LLVM. And we do see some people actually wanting to use LLVM, so Clang, as a C and C++ compiler for various reasons having to do with what they are wanting to do. And I guess at this point, we just say, well, if you want to use it, we need to make sure that our platform is well supported. So that's what we do. Now, what are we doing to support the platform? As I said, it's always sort of the two aspects. We need to support the ISA, and we need to support the microarchitecture. On the ISA, so the ISA, just as a refresher, because not everybody may be really familiar with the IBM Z architecture, it is publicly documented. There is principles of operations is the manual, big book. It's available. It actually has a history going back to the 1960s, and it's still compatible to back then. We don't support the very old stuff, but as I said in LLVM, we support everything starting from C10 up to the latest and greatest C14 processor. I'm not going into details. You can read the book, but just sort of quick overview. We have 16 general purpose registers, 6 floating point registers, which are now embedded into a 32-bit vector register file as of 2 machine generations ago. It is a sort of typical CISC architecture with some very, very complex instructions. But in general, every instruction sort of is available in a register-to-register and a memory-to-register format, which is, I guess, the characteristics of CISC. There have been more than 1,000 instructions for a while. It's been a lot more now. So we do support a variety of floating point formats, IEEE floating point, but also decimal floating point, and even some weird IBM thing like called hexadecimal floating point, which we don't support on compilers, but which the hardware supports. And now we do have vector instructions, as I said. Just sort of, if you're familiar with PowerPC VSX, it sort of looks similar what we do now. So we have the vector, we have the floating point registers, which were originally 16 of them. They were extended to double the size, and then we got another 16 registers. And now we have 32 registers, any of which can be used to hold the floating point value, but also they can be used to do SIMD operations both on integer and on floating point. And with the latest generation processors, we actually have a pretty wide supported set of floating point ISAs as well. The initial, the C13, only had double, but now we have a long double and single precision SIMD as well. Now, from a compiler perspective, it's really important to make sure that the ISA, sort of all the weird instructions, I sort of put it in quotes, are well supported, so that if there's a way to use an instruction that does sort of a more complex operation and it's still fast, we really want to make sure the compiler generates that instruction, right? That is one of the important pieces of getting good performance out of the machine. And so I'm not talking about the whole architecture, just wanted to do a little bit about some of these weirder parts and to see what do we do to support them. And one of the things I picked to talk about is the hybrid stuff, which is, I guess if you're familiar with the old Intel processors, where we had your AX register, which was 16-bit, and you could access both halves of them using AL and AH. And you could operate on those two separately, but you can also operate on the full AX. We now have somewhat sort of similar on the IBM Z, so we can, I just have the adds here. So you can add 1 to the 64-bit register, which is, of course, normal. You can also have an add 1 to the low 32-bit part, which is also sort of normal. I mean, that have most of the platforms that support both 32 and 64-bit have that. But we also have an instruction that adds 1 to the high 32-bit while leaving the low unchanged. And we have this type of instructions for a bunch of operations. And the intention was that you can use it to pretend you had 32-bit registers instead of your 64-bit registers, so that you don't have to spill as much. Now, this doesn't work out as well as we would have hoped. And in fact, right now, we are not. That's one part of the architecture that we are not supporting at all in GCC for various reasons, mostly having to do with we haven't had the resources to implement it.
So have you tried to use what IBM Z uses for the high parts? Like it's what's that strict low part?
Yeah. I mean, I think the infrastructure is there. I don't think there's anything particularly missing in the infrastructure. It's just that we need to implement it, and we need to implement it in a way that we don't regress code that isn't using it, because that's the main challenge. Because you have to basically rework. You have to pretend you have 32-bit registers. Sorry, you have to pretend you have 32-bit registers, right? And once you do that, the compiler is going to use all of them. And in many cases, it doesn't work because those operations will not be there. And that shouldn't cause any regressions anywhere. And that's sort of the big challenge. We did manage to get it going in LLVM, but that was sort of because when Richard started working on it, he started out modeling it that way from the very beginning. While in GCC, of course, so this was introduced in the architecture about 6 or 7 years ago, I think, if I remember correctly. And so the initial GCC port doesn't support that. And so from a GCC perspective, we would need a refactoring of all the stuff that's already in, which is always a little bit more difficult than if you just start out with doing it from the beginning. So as I said, there are challenges of having to do with once you tell the compiler you have all these registers, the compiler is going to use them. But then it turns out that, of course, many of the instructions aren't, in fact, supported fully across any combination of these registers, right? So it's one thing to have one of these registers in an operation. But it's getting more complicated if you have 2 of them, because then the register allocator can choose any variation. So you can have, like in this case, you can have a compare low half with low half, that's easy. High half with high half, okay, we have that. But high half with low half and low half with high half, we actually have just one of them. Because the architects thought we could save some instructions because who's going to need that? But from a compiler perspective, it means it's not orthogonal, and it makes it, yeah, we can work around that, but then that introduces extra overhead, and that introduces regressions sometimes. Because, of course, you always hit those workarounds just when you happen to be in the hot part of some important benchmark. So that's what makes it difficult. And of course, add has 3 register operands, which has 8 combinations, but we have only 3 variants of them supported in ISA. So even in LLVM, we don't support those. We just support sort of the general, sort of the moves and some of the simpler instructions. In GCC, as I said, right now it's not implemented. I don't think there's any fundamental obstacle. It would require a rework of the way we set up registers and set up all the stuff, what mode is allowed in what register and what combinations are allowed and whatnot, reload support and all the stuff that you need. Also debug info. Debug info, yes. Well, yeah. So, in fact, looking at that, it seems to me that actually it would be easier to support some of these combinations in GCC than it is in LLVM, because we do have the alternatives. So we can say, actually, we support these 3 out of the 8 possible combinations, and we don't support the other, and reload will, or LRA will fix it all up, which we don't have in LLVM, which I'll get back to later. So it might actually even be better. But given that we have it in LLVM, and it doesn't actually show a whole lot of difference, less than we thought, that has put it a little bit on the back burner. So, but at some point, when we don't have anything more urgent to do in GCC, we'll see if we can get back to it. And if there's any other weird architecture that has something like that we could take a look at, would be nice to know. AVR, okay. Now, so that was a weird part. That is a weird part that is sort of central, that we have to support and everything does, and that's the condition codes. And I mean, handling condition codes well is of course absolutely important for just about everything. And of course, every instruction has something like conditions, so you do a compare and you get the result somewhere, usually with flags or whatever. On Z architecture, we have what's called a condition code, and that's 2 bits, but it's not 2 flags. It's a 2-bit value, which is 0, 1, 2, or 3. And what it means depends on which instruction has set it. So if you do a compare and it returns a condition code 0, it means the 2 compared equal. If it's 1, it means the first one was low. If you get a 2, it means the first one was high. You will never get a 3. However, if you do a floating point compare, you get 0, 1, 3, which means the same, and CC3 means, well, the floating point values are unordered. You can't compare them. That's also not so weird still, but now you can do an add. And just like on Intel, if you do an add, you also get the result, well, the result is 0 or the result is negative. And you get that too. So you do an add, and the condition code will tell you, oh, I did the add, and by the way, the result was 0, or the result was negative, or the result was positive. Or you get a 3 if the processor says, I did the add, and by the way, it overflowed. However, if you get the overflow, it doesn't tell you it overflowed and now the value is positive or now it's negative, because it just tells you it overflowed. Because it just says 3. Well, that's one way, and if you add sort of an immediate, and you say, if I add a positive immediate, and it overflowed, I know it must be negative. So I can do the negative check by checking for negative or overflow. And then we have another add instruction that says add logical, which does the same which gives you the same result as the add. It just gives you a different condition code. And what it tells you is, actually, it uses the 2 bits basically as bits, and tells you the result is 0 or non-zero. And it tells you at the same time, we did have a carry, which means an unsigned overflow, or we didn't have an unsigned overflow. And so if you want to do that, then you can use that. Now, and then there's other cases like and, where you just get 0 or non-zero, and the others are never used. And then you get, I'm going to go into all of them, but One important one is test render mask, which basically does an immediate AND, so you give it a mask, an immediate, and it ANDs that immediate with your value in the register, and it says, well, all the masked bits were 0, okay, or they were all masked, all were 1, or they are mixed, but the leftmost one is 0, or they were mixed, but the leftmost one is 1. Which means, which is a way to get 2 bits into the CC, but it's also a way to do other interesting checks. And actually, it is very useful, and it often saves you an instruction. And then, of course, as I said, we have a Cisc architecture, so we have operations like convert UTF-8 to UTF-32 in one instruction. And it gives you something like, oh, I'm done, everything was good. Or it tells you, by the way, your destination buffer they gave me was too small. Or it tells you, well, your UTF-8 was invalid. Or it tells you, I did something, but I'm not done yet, call me again. So the compiler is never going to generate the last one, but it is going to generate any of the other ones and has to handle the condition code. There is instructions that then use the condition, which is, of course, well, I missed the most important ones. Of course, there's a conditional branch for the first thing. So you have a conditional branch that you can tell, well, branch to somewhere if condition code 0, 1, 2, or 3 in any combination was set. So you give it which condition codes do I want to branch, and if the condition is one of those, it branches. If it's one of the other ones, it doesn't branch. The same thing, we now have a loading condition with the same setup. If it's one of these values, then load or don't, otherwise don't. We can use the branch as a trap, so we have a conditional trap. And then we also have, in some of the more recent instructions, we have some shortcuts that actually bypass the CC, so we have a compare and branch, so it does the compare and the branch in a single instruction. We have something like branch and count, we have something like load and trap, so various combinations. And that's not so unusual, many platforms have combinations like that. But so what I'm trying to say is that it's really important to support these instructions and to make the best use we can out of all these various condition code values. And we implemented that both in LLVM and in GCC, and I'm not going into the details of all that exactly. I'm just trying to show that it sort of involves a lot of the different backend passes where to put it. And that's how we chose to do it right now in LLVM for various reasons, and we're still fiddling with it, and maybe it's not ideal and optimal. But one part of it is that it actually interacts with the fact that we chose to support the hybrid facility as well, because some of these operations are not available on high parts, but only on the low parts. So if we, for example, were to use a compare and branch early, it would force it to use low registers. So what we're doing is we leave it as compares early on and have the register allocator choose whether a low register is available or a high register needs to be used. And if it chooses a low register, then later on we compare it in a very late pass. If you have a compare and a branch, compare it to one instruction. But if a high register was used, we'll leave it as 2. Because the thought is, sort of from implementation microarchitecture perspective, a compare and branch actually isn't really faster than a separate compare and branch, because the instruction, the architecture will sort of internally split it again anyway. So it only saves you code size, not really execution time. So if using a high register saves you spilling, it's still preferable, right? But all these sort of pass ordering considerations make it a little bit complicated.
So is there a way to tell the register allocator that a low register could be preferable if available?
There are all sorts of ways you can tell the register allocator, but pretty much every time you do that, you get regressions somewhere else, because, you know, because you just have too little specific information. What you really want to tell it is if it is going to be used in a branch or in a compare later on, which it doesn't really always know. On the GCC side, it looks a little bit simpler, which is mainly because we don't support the high register part, which is one of the reasons why adding high registers is complicated. And it also looks simple because right now pretty much everything really is done in Combine, which is nice, but then also maybe not. I mean, depending on whether Combine will find it. So, and I have a specific example. So I have a specific test and a mask example that we can look at in detail maybe later on. So
I'm using the compare elimination path. You're not using that because you're still CP0 or?
No. Yeah, we probably use the compare elimination path as well. I didn't list. Yeah. Yeah, that's right. Yeah, that's right. No, of course you can't do that with CC0. we need different CC modes to tell which sort of, because depending on which compare you use, you need to use a different branch, and you need to have the CC mode that tells you. And so.
So how many modes?
20, 30, something like that. So I have to check a lot. Some other just miscellaneous stuff that when I looked at both and said, well, what's interesting to talk about? Well, decimal float may or may not be interesting depending on whether you need it. GCC supports it, and so we do in the backend. LLVM does not because it just doesn't support it in the generic code and in Clang. So nothing we can do here. Inline expansion of string and memory functions is always a topic, depending on architecture and sometimes it seems to be, it's better to expand, sometimes it's better to not expand. Right now in LLVM, we only expand them if for known length. In GCC, we try to expand them also often for unknown lengths using various other special constructs that we have. We don't do that in LLVM yet, and it's not really sure if it's a good thing or not, but something to look at. Another weird instruction we have, well, maybe not so weird, PowerPC has it too, is the rotate, then insert selected bits, where you can tell in one instruction, take a value, rotate it, use some of the bits, and insert them in that place into another value, or them, add them, XOR them, which is sort of, you can combine 2, 3, sometimes 4 instructions in one, so it's important to use them. In LLVM, we do all that with C++ code that looks at the whole tree and finds good combinations. In GCC, we just do it in Combine. So there are cases where we find more in LLVM than we find in GCC. It's better now that Combine does 4 in 1, so that's good. But there may still be some rare cases.
Combination reorg, or where you would do it if you wanted to get a bit more bits?
I don't know. So we used to see a lot more cases where LLVM found something which we didn't, and we fixed those by offering intermediate patterns for Combine. So that Combine combines it into one pattern, and then that pattern gets then combined with other patterns, so forth. That's the way we did it, yeah.
It's what we do in PowerPC.
Yeah. So it's tedious because you have to write all these patterns for Combine, but yeah.
You have more instructions than
Yes. Yes.
over to shore and whatever. And that probably adds a lot of complexity.
Yeah. Another sort of minor difference is that in LLVM it's really hard to say we support integer types in floating point registers. In GCC we do that. We can't really do any operations on them, but we can use them sort of as extended spill slots, so you can move GPR into an FPR to just store the value away. Right now we don't do that in LLVM, so not clear if that's a big deal, but it is a difference right now as well. Okay, I need to move ahead a little bit. That was just a few highlights, and of course, it's a complicated architecture and there's many different things. I hope I picked some interesting topics to talk about, but there's a whole lot more we could talk about. But I also wanted to talk about microarchitecture optimizations. Now, the microarchitecture, of course, is not generally public, but as of a few years ago, we actually do have a quite detailed public document, namely this one, which is specifically written by actually one of the leads of the microprocessor development with a target audience of compiler developers. And it does tell a lot of the things that the hardware people think compiler people should know or might want to know. And we work with them to get more stuff in if they don't always get it right. And this was first put out for the Z13 a couple years ago, and now just this year was updated for the Z14. So, well,
something about speculation in there?
not talking about that. So, and it does have things like, and that's just sort of copied out of the document. So if you're interested, that document is public, you can just download it. And it has things like this diagram on how execution works. It's not sort of very surprising. It's sort of like most current high-performance out-of-order processes work. So you do have your branch prediction, you have which sort of determines what the processor thinks is going to get executed. It then fetches that, decodes the instruction. It has a decoded instruction buffer, and it then pushes those into issue queues where the out-of-order magic happens. And sorry, it has them in the decode buffer, and then the out-of-order magic happens, and they get pushed into the issue queue from where they are issued as soon as all the dependencies are ready onto the execution units. And we can push up to 6 instructions per cycle into the issue queues, and we can issue out of the issue queues up to, I guess, in theory, 10 per cycle, but 2 of them have to be branches, and the 4th of them have to fit all the various different execution units, which basically never happens that you get 10, but in theory you can get up to 10. And then we do have load store units for memory access. We have 2 integer units and on each side, and we have 1 vector unit, which does vector and floating point. And that all that is duplicated into basically 2 sides. So 2 sides of these. And that's there's some more detail in sort of the various latencies and where we have bypasses between various units. Not going into detail of that, just sort of when you're talking about then instruction scheduling, what aspects of the architecture do we want the compiler to handle? And the first, to make it clear, again, that's not very surprising, we cannot, like on any of the modern out-of-order processes, we cannot model the actual execution phase because we can never know when the things issue, because it depends on is it in cache or not and whatever, so that's just not predictable for us. But what we can do is we can optimize for the decoder grouping so that at least sort of getting the instructions up to 6 per cycle into the issue queues only works if we can get full groups of 3 instructions for each side. And there are various rules, like, for example, where branches may be within that group of 3, and some instructions are cracked into multiple micro operations and so forth. And all that is deterministic enough that the compiler can actually do an instruction scheduling that optimizes the size of the groups that we will get out. And again, that's not particularly surprising, probably because, I guess, for Intel and PowerPC, it's all similar. But that's not the only concern. We're also trying to make sure that we sort of mix things up so that we don't just have all integer instructions, like 100 of them, and then 100 floating point instructions, because then even the out-of-order logic can't do anything. But we want to sort of mix them up to give choices to possibly fill all the various units as good as possible. And there are some special cases, like, for example, and now let me go back to this here, where it's this weird loop, which is the one case where we actually have some instructions that are not fully pipelined, which is something like a floating point divide or square root, where depending on the exact number you get, you may run many times through this cycle. And while it's doing that, it can't do a second one. But we do have 2 sides, so we have a second of this unit on the other side. But if we got 2 divides into the same group, then they have to be issued to the same side. So the one side will be busy with executing the first, and the other side will be idle, even though it could have executed the second one had we just scheduled them in another group. And that's what we can do. Okay. Now, do we do that? Yes, we do, both in LLVM and GCC. In GCC, we've been doing that for a while. In LLVM, sort of just now, if you watched the commits, we are still doing scheduler fixes and scheduler commits, but now current mainline pretty much has everything in there as well. We do have two scheduling passes, one after register allocation, one before register allocation, same as in GCC. All the decoder grouping is done post-array because we need to know the exact instruction sequence. Pre-array, we want to do some sort of mixing up and considering latencies, but we don't mix up stuff too much so that we then get spills. Again, same problem as many other platforms and same problems between GCC and LLVM. Implementation is, of course, different, but sort of pretty much at the same level right now. Well, the one thing GCC does extra, of course, is we do still have the in-order scheduling for the old processes, which we don't do in GNU.
So one question, would you think that pre-register allocation scheduling could be done on a higher level intermediate language, like in GCC on Gimple?
Maybe. So really the only point of that is sort of to try to make sure that we don't force things too close just because we already have decided to choose the same register for two independent things. If we hadn't made that choice, we could have moved floating point in between, but or we could have moved. So it's about getting latency chains short. And I have to think about it if Gimple is. I guess part of that could be done in Gimple. I don't know.
I'm not sure how it's done in LLVM.
Yeah.
Something like attuning.
I get to that in a minute.
Yeah.
I get to that in a minute. But it's not. It's also done on the low level in LLVM. Okay, let's move on. A couple of other things. I mean, instruction scheduling is not the only thing. There are other things like loop unrolling, which turned out to be pretty important. In particular, it turns out a very small loop tend to, well, it's not like the processor can't handle short loops. It's just like if there is any problem and it also is in a short loop, then the processor generally can't recover fast enough to make sure then things blow up. So in general, it turns out, at least for us, for our current implementations, it is better to avoid very short loops if they are hot. And that's actually one part where LLVM currently does better than GCC. Because in GCC, we can unroll loops, but only if we know enough about them to at least pre-compute iteration counts or whatever. In LLVM, even if we don't know anything at all, it will still unroll. It will just duplicate the exit check as well. So
we have that in GCC as well.
we have that now?
Yeah, it's basically unroll all loops that is exactly that.
But even unroll all loops doesn't duplicate the exit check, I thought.
Very well. Yeah. Unroll all loops, it just peels and then have an unroll inner loop.
Yeah.
So it's not the very same.
I think there's a mode that maybe it can't be enabled anymore.
Yeah, I think in GCC you can peel if you can compute the loop count at runtime, but LLVM will even unroll loops where you can't even pre-compute the iteration count at runtime. So, right. Other issues like, what? Not me. Other issues with loop strength reduction where we need to make a bit careful because the vector instructions, the vector loads don't support all the addressing modes that the scalar loads support. So when choosing induction variables and then vectorizing, LLVM did get it wrong. I think in GCC it was better from the beginning. In LLVM we actually had to add a new common code hook to fix that. Cost functions, function alignment, pretty much standard stuff which we did across both platforms. in general, I guess the first bullet will be familiar to pretty much everybody who's working on a modern, complicated processor. Sometimes you change something where you think it obviously looks better, but then you run it and it's slower because of whatever second-order effect happens on the hardware. But sometimes you ask your hardware designers and they don't understand it, and then they investigate and then say, oh, well, yeah, because there is this shortcut here and it doesn't work in this case. So it makes things complicated in general. But okay, now after having talked a long time about the type of things we are doing, now what's the result? And this is the chart. So they are all measured on C13 because I had longer history going back on C13, and the red bar is spec, just not official numbers. The red line is LLVM over time, from the very first until just right now. No, it's not 0. It's not 0. It is. No, it's not based at 0. So the
version 0 for all layer.
yeah. We used to be about that at that time was about 15% slower than GCC at that point, and as you see, we had some period of time where we actually had better overall results in LLVM than GCC at the time. GCC 8 has caught up and overtaken us again. Now, why did we get these results? Well, as to the best of what I was able to find out, what we did and what we think caused these changes, I put it on here. So let's start with the LLVM stuff. The 3.3 was the initial version that just worked correctly. It didn't use all the ISA, it didn't have any scheduling, it has nothing, it just worked correctly. Now this big jump here was in 3.4. We actually started using things like test on a mask and any of these more complicated instructions. So that was the big jump here. 3.7 we actually added the vector instructions, but didn't tune the vectorizer yet. That's why you only see a small bump here. Then I don't know what happened there. Then actually in LLVM 4, we for the first time did any scheduling and microarchitecture tuning at all. In 5, we then tuned the vectorizer, that's what made us go better than GCC at the time. And the last bump we just got a few weeks ago was actually tuning the inliner to make decisions that are not all based on measuring on Intel, but also actually based on measuring what's good for our platform. Now on GCC, of course, we had been optimizing GCC for 15 years at that point already. So with GCC5, we added C13, the vector instructions, and scheduling. We did some more vector tuning, which also helped on GCC. And actually, the big jump here in 8 is not something we did at all. It was a common code change in loop distribution. And if you're wondering why that helps, maybe in the next chart we'll explain. Because it makes Hammer go twice as fast as it used to go. So basically, the reason why GCC now is better again is because Hammer is now twice as fast in GCC as in LLVM. But that's not because LLVM can't do loop distribution. It doesn't do it on this test case. If you just add the pragma, it will also be twice as fast. So we only still need to figure out why it doesn't do that by default in this case. Yes. So once, and that's actually, that is the sort of, if you look at the latest state here at the very end, so the current GCC and the current LLVM split across the various spec cases. If you ignore the Hammer for now, there's one other case where GCC is still better. And this is one case, again, where LLVM does an SLP thing and vectorizes, but the result is worse than not doing it. And GCC doesn't do it, so it's, again, probably just a cost model thing.
So is it with O2 or?
Yeah, well, it's all O3, all O3. It's just plain O3, no magic spec tuning, whatever. We just do O3, right?
But it's also only spec
It is only spec int, and the reason I'm not showing spec fp is because, first of all, we don't care so much about that, and also we have no Fortran in LLVM, and that makes the comparison always weird. But everything else, interestingly enough, right now on Z, all the other cases, we see LLVM is better. And that didn't used to be the case. That is only the case since this last bit of inline tuning. And because that's only been that way for the past few weeks, I actually don't really know why exactly this now happens. So this now gives opportunity for the GCC side to maybe catch up again.
So I guess inline tuning means there are some magic numbers you can tune, and you did some machine learning to get the best numbers. And
no.
So, or did you try to invent numbers that make sense?
Well, this particular case, they just have sort of a factor where they do all their thing and then say the target, you can give us a factor by which to bias those numbers. And we just say factor 3. And we just measured 1, 2, 3, 4, and 3 was the best, and that's what we get. So it was a one-line change. It inlines more. Yeah. It inlines more, yes. Because it was all tuned for Intel, and on Intel, function calls are pretty fast, and on our machine, they are not quite as fast, so inlining more helps more. So that's pretty much it.
And is there any plan to tune the inliner for GCC on? Is there any plan to tune the inliner for GCC on Z?
We did tune the inliner for GCC a long time ago. We can maybe look at that again and see if there's no. Yes, and we will need to do that, yes.
We don't have the convenience factor, but we can add it.
We have other parameters. Yeah. Okay, now I guess we're sort of running out of time, but sort of this is really, I mean, now we really need to find out what's going on there and use that as an opportunity to catch up again with GCC. So for the past 3-4 years, we've been playing catch up in LLVM. Now we'll need to see what's going on here. Okay, maybe just very quick, maybe skip some of the details, but since you were asking that, sort of, I guess when looking at how does it feel working with the compilers, the most important part is sort of how do the intermediate representations look like, right? And in LLVM, we really have sort of these 4. There's the LLVM IR, which is sort of that's what LLVM is famous for, and that is sort of like what Gimple is for GCC. And in the back end, we don't really work much with it because sort of that's where we start and everything. But that's where all the higher level stuff operates on. But in the back end, we start translating LLVM IR first to what they call the selection DAG, which is then used for instruction selection within a basic block, which is sort of like what RTL, higher level RTL would be in GCC as it is used in expand and combine, except that it's still in SSA form. And this runs the selection, and I have more on that in a minute. And after the selection is done, we are at a level what they call MI, which is machine instruction. And as the name says, every MI is sort of supposed to represent one machine instruction, target instruction, which is again sort of like what RTL is in GCC, except if you think of RTL that only has register, memory, and constants, sets, and clobbers, and everything else is unspec. So it has no known semantics. It has no add, and, whatever. It just has sort of the operands and the data flow and the control flow. And it has sort of, yes, it describes which instruction it is, but the common code doesn't understand any of that. It's just like an unspec is for GCC. And so all the stuff that common code understands happens on the selection DAG. And everything else, so if you want to do any more optimization on the MI stuff, it's really all up to the target to know what the instruction is and can it be combined or can it be modified, and it's all in target code, usually in C++ code in the target, which has its good sides because you can do a lot of stuff, but also you can't just like call a simplifier RTX that doesn't exist. And finally, there's one fourth stage which doesn't exist in GCC because in LLVM we actually go all the way down to binary code. And there's the MC layer that does that. It's used for assembling, disassembling. And that sort of would correspond to some of the data structures in GNU Tools. Now, one note on documentation, the LLVM. So people say LLVM is extremely well documented, and that's true for the LLVM IR. It really is. The lower part, selection diag, MI, I would say less so. So I've had to read the generator programs that handle that stuff a lot to understand what's going on. On GCC, I would say it's the other way around. The RTL is very well documented. If you look at the RTL, MD, you know what RTL is. Gimple, maybe less so. I don't know if it's better now, but so I guess that's where you see where both compilers came from. So from a backend perspective, I don't really agree with the statement that LLVM is easier to use because it's so well documented, because it's not true for the parts that the backend really uses. So that said, in general, things look similar. You have passes that do more or less the same things. You have MD files in GCC. You have TD files in LLVM, which are used to describe the instructions. And it's sort of, I guess, on a high level, they are the same, except for the syntax. The MD file pretends it is Lisp. The TD file pretends it is C++ templates. Now, depending on what you prefer, you may find the one or the other easier to use. But in general, it does the same thing. It's both C++. Of course, GCC is sort of, at least in the backend part, it's sort of actually just C that is compiled to C++ for the most part, really. While in LLVM, it is C++ 11 and uses templates and all kinds of stuff. So it is different. And that's sort of more of my subjective view. I don't know. LLVM Z seems to provide more flexibility. You can more stuff. I want to do something special. You can just do it. In GCC, it's better now. We can now also add random passes in GCC. So, but you still usually don't do it. Well, in LLVM, you do it. But on the other hand, the drawback of that is that, yeah, you have to write a whole lot of more C++ code in LLVM backend than you typically do in a GCC backend. One major difference, as far as the backend sort of look and feel is concerned, there is no reload, which is, yeah, on the one hand, people complain about reload, or whatever, LRA, but it sort of has the same. So the main difference is that in GCC, you have this notion of, on the higher level RTL, you have your predicates. You can accept all kinds of different operands in the same instruction. And then after reload, you choose one of the alternatives. And so you can have, I have an instruction that does an add, and it can be either a register, or memory, or immediate, or whatever. And after reload, it chooses which one. You don't have that in LLVM at all. You have MI, and you have an add register, and you have an add memory, and you have an add immediate. And they're all three unspecs. The common code doesn't know anything about any of them. So if you do things like register allocation, and then you spill, and then you say, well, I had it in a register, but now it's in memory. So wouldn't it be nice to now use the other instruction instead? Well, you can do it, but only if you have code in your backend that says, oh, this was an add register, and it is now spilled, and so I can now turn it into an add memory. So it's a bit more tedious. Yeah, and of course, also what makes an LLVM a bit more tedious is, of course, you actually have to have support for all the binary stuff also in the same file, which has its good parts because you now have sort of in the assembler and disassembler, you have some sort of high-level semantic information too. So the disassembler can just say, oh, I know this is a branch because my LLVM data structures for the compiler tell me that instruction is a branch, so that's nice. But yeah. So I guess we're running out of time, so I'm not really going to talk about the platform API. As I said, list of passes, more or less one-to-one mapping, sort of, not really, but in general, you have passes that do the same thing in GCC. It's not surprising because it is a compiler and needs to do the type of same things. And yeah, just as a small example, I tried to find something simple. And so I came up with a Pieceswap because that's sort of not related to anything else. So that's actually GCC MD file for Pieceswap. It defines 6 instructions using a mode macro, which sort of duplicates the thing into 2, and then it uses alternatives with 3 instructions, depending on the operands. In the LLVM file, I have the same 6 instructions, which are 6 separate patterns, but it sort of, to avoid the duplication, what you would use in LLVM is use things like this unary RE, which is another basically sort of template-looking thing, which you define earlier in your TD file, which then get instantiated with those particular arguments. So the GCC way of avoiding duplication is like the alternatives and then those mode macros, while the LLVM way of avoiding duplication is to abstract the duplicate stuff into these sort of template classes, which are then instantiated. And so this has all the information about, well, it has sort of a set with one, it does an operation with one operand and get one result. And then the instantiated values here tell it what operation it is and what the register size is, register classes are, and then here what the binary machine code or opcode is. Yeah, go ahead.
Which one is easier to debug in terms of instruction definitions?
Neither. I must say I've had to debug the generator tools that sort of, both in LLVM and in GCC, we have generator tools that read that file and create source files from it, right? And in GCC, I pretty much never had to debug those generator tools. In LLVM, I need to debug them relatively frequently to understand what they are doing. But in general, I mean, it's both complicated. Okay. So I wanted to show a little bit of detail on that's the test case I had to show why the test under mask is useful. So if you look at that if one flag bit is set and the other flag is not set, then do something. And that is one test under mask and then one jump. And this same code we get now both with GCC and LLVM. And I could go through sort of the various intermediate stages to see how it looks and where it is done. But sort of unfortunately, I've run out of time. I guess given that we are out of time, I would sort of conclude the official part of the talk now. If anybody is still interested and still has time, I would be happy to go ahead and run through those details later.
I'm not sure how much time we have.
Oh, okay. I see. Okay. Okay. Good. Otherwise, any further questions?